Thanks, Stace. So it's still late morning here at Stanford and in the David Rumsey Map Center. So this next panel, let me step back. We've heard a lot about this project, machine reading maps, and it's often described as search within maps or even like OCR for text documents. But of course, that's a descriptive concept that people understand, that resonates with people immediately. But it's, as you will see in a moment, it's much, much more than that. We've also seen this morning machines reading maps depicted as a visual display of search results, as we see on the screen right now. This is an experiential concept that people also really resonate with, right? But the visualization, of course, relies on all of these other pieces coming together. And that's really what this panel is going to be about. For researchers who work with these maps, there might be an inclination to say, well, this is all well and good, but just give me the data, right? But also the data alone is not going to give you what machines reading maps is. So the morning sessions for the summit, both today and tomorrow, are really about building a developer community. So understanding how all of the different pieces come together and are integral to the whole is essential for this. So this panel right now is looking under the hood at what is a very complex, coordinated effort that has made machines reading maps possible. To make what you're seeing today possible involves the work of different teams, each of which is extraordinary on its own, but together produces something that's much bigger than the individual parts. Right? You're going to hear from the map processing team. You're going to hear from the visual browser team, and you're going to hear from the annotation team and the conductor who brought this whole big picture vision together. So we're going to begin with Leeje Jang, who's representing the mapKurator team from the University of Minnesota's Knowledge Computing Lab, which is directed by Jang. This work, this is the work that has advanced efforts exponentially, and the rest of the team is just entering right now. This is the work that's really advanced what were the early efforts at crowdsourcing annotation, right, or hand annotation. This is like, we've moved way beyond that, and now you're going to see an annotated pipeline that can, with remarkable accuracy, identify text within maps. So Leeje is a first-year PhD student at the University of Minnesota, working with this Knowledge Computing Lab, which is directed by Associate Professor of Computer Science and Engineering, Jang. Leeje's research focuses on computer vision with machine learning, especially machine learning models based on GIS. What is of greatest interest to Leeje in this project is the multilingual text spotting. And work continues on this aspect of the project as David Rumsey mentioned earlier. There will be advances in language support in version 3. And now I turn it over to Leeje.
Hi, I'm Leeje. I'm a first-year PhD student in University of Minnesota, and I'm very glad to introduce the mapKurator system, extracting and linking text from large numbers of scans maps. And I'd like to say thanks to David Rumsey and other collaborators to supporting us this wonderful experience on this project. So. This is our overview of today's presentation. I'm going to start with map processing with machine learning and the goal of the mapKurator system, and I will describe overall pipeline of the mapKurator and open source code and documentation, and I will end with the mapKurator webpage. We develop machine learning technologies for extracting information from scanned maps. For example, we extract geographic features using geographic features from scanned maps. We build machine learning models for extracting lines, points, and polygons from scanned geological maps. So we won 2002 Darfan Map Geographical Feature Extraction Competition. And the other thing is that we extract map text information from scanned maps. So we build machine learning models for text spotting from maps, and we also build machine learning models for linking map text. The goal of the mapKurator system is to find relevant maps and make their content useful, which is easily searchable and support complex queries. For example, we find all maps from the 19th century UK, which covers at least one church until 2 hospitals within a 5-mile radius. Also, the other thing is to easily convert map content to useful data. I'd like to introduce the mapKurator pipeline. The mapKurator pipeline divided into 2 big parts. The one is text detection and recognition, and the other one is the post-OCR and entity linking. There is 4 inputs in the mapKurator pipeline. The one is the integrated metadata, which contains the ground point pairs, which are used in generating a geocoordinates. The second one is map images, and the third one is ground truth annotation, which are used for evaluating the text spotting module. The last one is knowledge bases, which are used for post-OCR and entity linking. I will go more through into the mapKurator pipeline. First, we use image cropping module, which generates image patches. And the next step, we use patch text spotter, which generates patch level text detection and recognition. And the next step is we use patch to map merging, which merges text detection and recognition results with image coordinates, and the format is GeoJSON file. And we use a geocoordinate converter module to merge text detection and recognition result with a geocoordinates. And the last step is we use post-OCR and entity linking for using a knowledge basis, which improves the text spotting result and includes the information from the real-world OSM database. This is an example of result of image cropping model, and each of the image patches are in the same size with 1000 pixels and 1000 pixels. And Yijun will present more in detail about the text spotting. So let me introduce Yijun over here.
Thank you, EJ. Hello, everyone. My name is Yijun Lin. I'm a PhD student in Knowledge Computing Lab, and I'm working on this text spotting model for the historical map text detection and recognition. So in the mapKurator system, we provide 2 spotting models. The first one is TestR, which was proposed in 2022. It's a state-of-the-art machine learning model for text detection and recognition, but it was proposed for detecting the text in the scenic photos. And then we proposed a new model called Spotter V2. In this model, we present a novel feature sampling strategy that is able to find more relevant image features around the target point for predicting the boundary points. And this gives us more accurate detection and recognition performance. And we use this model trained with the synthetic data set. The first one is CMap, which is we created that for mimicking the style of historical map for text detection and recognition. And the other one is syntax, which was a method proposed in 2015, but it's also built for like detecting text in scenic photos. And we are also able to fine-tune the model with human annotations, but at this point we only have English ones. And our spotting model currently support for multilingual text spotting, including English, Arabic, Russian, Chinese, and Japanese. So I would like to talk more about our synthetic map datasets. This is really important because to train a machine learning model, we typically need a lot of training samples. and manual annotation will not be able to do that. So we create a synthetic map dataset to use the location names from other datasets, such as OpenStreetMap dataset or historical gazetteers. And we are mimicking the text and background styles from those real historical maps. And this approach is generalizable to various languages. So the image down here are all the synthetic map images, and they're in different languages and different backgrounds. And another data resources that I want to point out is human annotations. Human annotations is really important for training and testing. So in terms of testing, they're really great resources to quantitatively know that if our spotting model is good or not. And currently we have three resources. The first one is introduced by Katie, is Edinburgh Maps, and it has more than 30,000 annotations, which is a good annotation data set for evaluation. And the second one is 30 maps annotated by Wayman's group. It has 9 styles of maps. And from our group, we also annotated 300 map patches from 54 maps because we want to see how is the model perform on like more diverse maps. But these maps are all used for testing. And if we want to use those annotations for training, there's some like annotation convention that we have to follow. So I put an example here that is the annotations that we can use for training. And if we can, if we have 16 boundary points that are close to the text, and there are 8 points evenly distributed for the top and bottom curves, and it has to be clockwise. So basically it has to start from the blue points and end with the green point here. And also to be able to use those maps for training, we need to cover diverse map styles. And on the left-hand side, there are the example annotations from Edinburgh Maps, and they're really good resources. If we want to use those annotations for training, we need to do some manual post-processing on those annotations to be able to fit for our model. So this is the introduction for text spotting and the training data set we use and the human annotations we have. Thank you.
Thank you, Yujin, for the presentation. And I will continuing with the result of module 3, which is patch to map merging. This is the visualization result of image patch and text detection results. And we can see that the result is merged from the image patches to the entire map. And as we mentioned earlier, we support multilingual text spotting, and currently we're supporting 4 languages. The one is Russian and Arabic, Chinese, and Japanese. And these are the results, examples of text spotting result with multilingual. The first one is Russian, and the second one is Arabic, and the last one is Japanese. This is the result of geo-coordinate converter module. As you see in the left side of the slide, this is an output file of module 3, which generate image coordinates. Comparing with the module 3, the output file of the module 4 generates geo-coordinates within the properties and the geometry coordinates. And this is a visualization result of geo-coordinate converter using QGIS within the base map. And for the post-OCR and entity linker module, we can see that in the figure, there is a text with Wawina, and the post-OCR label improve the text spotting result based on the edit distance and the popularity of the Word OSM database. And for the OSM ID property, we can see that it includes a list of OpenStreetMap features stored in PostgreSDB. And this is the year-end summary of David Ramsey project for our site. First, we did version 1 results on September 22, 2030. September, so we had an initial test run for the mapKurator pipeline with the test R. The second version is January 2023, and we did a mapKurator with the Spotter V2. And currently, we are running a mapKurator with the Spotter V2 trained with human annotation with the English, and also we're in the processing of generating multilingual text spotter within the Russian, Arabic, Chinese, and Japanese. And we also did fine-graded training for text spotter, and we did a mapKurator system with documentations. And for the open source code and documentation, we had an integration with Recogito, which is published on Docker Hub. And the code is released to GitHub repository, and the documentation with tutorials are in our website. And this is a screenshot of Recogito interface. And in the figure, we can see an example of bounding box modification, which means that we can directly modify the annotation result, which is come from the text spotting. And I would like to introduce our webpage. First, and as you see in the right upper part, you can go directly into the GitHub through this link. And on the left side, there is detailed description about what the mapKurator is, and the detailed description of each module, starting from image cropping, patch text spotter, and patch to map merging, and geocoordinate converter, and post OCR, and entity linker. And currently, we support 2 versions of mapKurator. The first one is standalone mapKurator, and the second one is mapKurator with Recogito. For the Ramsey customized standalone mapKurator, we use a map image and control point pairs as an input based on the format of Ramsey map collections format. And it generates the result of image coordinates and geocoordinates as a GeoJSON files. And for the mapKurator with Recogito, we use a map image and map tiles as an input and generates a mapKurator output directly on the Recogito UI. And the more detailed information about standalone mapKurator and mapKurator with Recogito are well described in our webpage. Yeah, this is what I prepared for the presentation. And here the QR code link to go to the mapKurator webpage. And if you're interested in trying mapKurator, feel free to reach out to me. And thank you for all the sponsors and collaborators and all the contributors in our members. Thank you.